Good. Hello, science students. Our third lab was a set of water activities, and your goal for the first one was to take the paperclip and set it on top of the water. Uh, I found that it's actually easier if you push it in from the side instead of what I'm doing here, which is kind of pushing it in perpendicular to the side of the mug. And if you do it just right, what happens is the surface tension or the cohesion of the water is strong enough that the paperclip's weight doesn't break those bonds or the connections between the water molecules, and it sits right on top. If you look really closely, you can actually see the water kind of bubbling up underneath the paperclip and holding it up there. Clearly, the paperclip is more dense than the water, so it should sink, but because the cohesion or the intermolecular forces between the water molecules are so strong, you can get a paperclip to sit on top of the water just like this right here. It'll even kind of float and move around without dropping. It'll stay there for a really long time, usually not dropping until something bumps the cup. The second activity is your water versus oil drops. So water is polar, oil is considered nonpolar. This means that the intermolecular forces between the water molecules are usually a lot stronger than the oil molecules, and you can kind of see this. So with the water here, you can see it doming up and making this bubble kind of shape on top of the penny, and eventually there's so many that it bursts. I was able to get about 45 going pretty quickly. The oil drops, a little bit different. It bubbles up, but it breaks relatively quickly with only 22 drops because the cohesion is much weaker. And you can kind of compare that in the two side-by-side shots here. Finally, we have our water cups and strings. So first time I try this, I do it with a dry piece of yarn and doesn't go particularly well. You'll notice that as the yarn gets damp or wet, the water seems to make it a little bit further down the string, but for the most part, very little water is moving along the yarn and it's falling down. So there is some adhesion happening here where the water is sticking to the string or the yarn where the water is sticking to another substance. And it is getting a little bit better as we go, but it's not great. We try it one more time. This time I'm going to get the yarn wet. And what this does is we are now having adhesion and cohesion work together. The adhesion is keeping the water in the yarn, so just kind of like a damp piece of paper, the water is sticking to the particles in the yarn. But now when I pour it down the string, the water doesn't just have the yarn to stick to, it has the water in the string. So we're taking advantage of both cohesion and adhesion, and you can see once I get it going, I have quite a bit of water at the bottom of that yarn going all the way down and falling right into the cup there. You'll notice that I turn the other cup kind of around backwards so that the water falls into the cup. It doesn't just hit the front of the cup and fall into the sink. So this one uses adhesion between the water and the string, and then cohesion between the water and the string and the water running along the bottom to make sure that the water can make it all the way down to the bottom of the cup. And water being polar, it has these really strong intermolecular forces, which explains all three of these activities.